Hey folks, this is Bhavya Patel. I am a student of DISCT. Currently, we are working on a discrete mathematics project which is data compression. Inspired by Professor Manish Kumar Gupta, Professor Prosenjit Kundu, and Professor Manoj Rath. And this is our team. These are contents. Why data compression? In today's digital era, the exponential growth of data has created an urgent need for efficient data management and utilization. The ability to store, transmit, and process large volumes of information has become a critical challenge faced by individuals, businesses, and industries alike. In this context, data compression emerges as a powerful solution that enables us to effectively address these challenges and maximize the potential of. What is data compression? We'll talk about this image later on. Data compression is the process of reducing the size of the digital data without losing its essential information, achieved through the use of algorithms and techniques that eliminate redundancy and irrelevant details. Here are some key benefits of data compression. First is reduced storage space. Data compression significantly reduces the amount of storage space required to store data, allowing for most efficient utilization of storage devices. Second is faster data transfer. It is obvious that compressed data requires less time to transmit over networks or transfer between devices. Third is lower bandwidth usage. Compressed data consumes less bandwidth during transmission. This benefit is particularly relevant in situations involving internet connection, mobile networks, or data intensive applications. Fourth is improved system performance. Data compression can enhance the performance of computing systems by reducing the amount of data that needs to be processed. This leads to faster data access, improved response times, and more efficient resource utilization, particularly in environments with constrained computational resources. Fifth is cost saving. By reducing storage requirements and optimizing data transmission, data compression can result in cost saving. It helps minimize expenses associated with hardware upgrades, network bandwidth, cloud storage, and other related resources. Sixth is data backup and recovery. Seventh is increased capacity for data analysis. Eighth is preservation of data integrity. There are mainly two types of data compression techniques. First is lossless compression and second is lossy compression. Lossless compression. Lossless compression is the compression technique that allows the exact reconstruction of the original data from the compressed version without any loss of information. The goal is to represent the data in a more efficient form without sacrificing data integrity. Lossless compression algorithms typically achieve compression by exploiting redundancies and patterns in the data. Key characteristics of lossless compression. First is preservation of data integrity. Lossless compression ensures that every bit of original data can perfectly reconstructed. No information is lost during the compression and decompression process. Second is exact reversibility. The compression and decompression operations are reversible, resulting in an identical copy of the original data after decompression. Third is common techniques. Lossless compression techniques include Huffman coding, arithmetic coding, runtime coding, and Lempel-Zwiebel's known as LZW algorithms. Applications of lossless compression. Text and document compression. Lossless compression is commonly used for compressing text files, documents, and program files. Data transmission and archiving. Lossless compression is crucial for efficient storage, backup, and transmission of data while maintaining its integrity. Scientific and medical data. Lossless compression is often employed in applications that require exact preservation of data, such as scientific research and medical imaging and data archives. Lossless compression algorithms. There are different kind of algorithms available out there like Huffman coding, arithmetic coding, RLE, LZ77, LZMA, LZH, Snappy, Quick LZ, Brotli, LZ4, LZSS, LZW. But we'll learn only three algorithms today, which is Huffman coding, RLE, and Lempel-Zwiebel's known as LZW algorithm. Let's learn about lossy compression. Lossy compression is a data compression technique that achieves higher compression ratios by sacrificing some amount of data fidelity. It removes non-essential or less significant information from the data, resulting in a compressed version that cannot be perfectly reconstructed to the original data. The goal is to discard data that may not be noticeable to human perception or deemed less important for the specific application. Key characteristics of lossy compression. First is irreversible compression. Lossy compression permanently removes certain data components, making it impossible to reconstruct the exact original data. Second is trade-off between compression and fidelity. Lossy compression aims to strike a balance between achieving high compression ratios and maintaining acceptable quality for the intended application. Third is lossy techniques. Lossy compression techniques include transform coding. Example is discrete cosine transform in JPEG, quantization, perceptual coding, and psychoacoustic modeling. Example in MP3 audio compression. Applications of lossy compression. Multimedia compression. Lossy compression is extensively used for compressing multimedia content such as images, audio, and video. Formats like JPG for image, MP3 for audio, and MPEG for video employ lossy compression to achieve high compression ratios while maintaining acceptable quality. Streaming and broadcasting. Lossy compression is crucial for efficient transmission of multimedia content over networks with limited bandwidth, enabling real-time streaming and broadcasting. Third is data analysis and machine learning. Lossy compression is sometimes used to reduce the dimensionality or size of the large datasets without significantly affecting the accuracy of subsequent analysis or machine learning tasks. Let's understand about different lossless compression algorithms. First is run length encoding. Run length encoding (RLE) is a simple yet effective lossless data compression algorithm. It works by replacing consecutive occurrence of the same data value with a count and the value itself. The algorithm is primarily used for compressing data that contains long runs or repeated characters or symbols. Here is how RLE works step by step. First, input data. RLE takes an input data stream which can be a sequence of characters, symbols, or pixels. Second is encoding. RLE scans the input data from left to right. It identifies consecutive sequences of the same value. For each sequence, RLE counts the number of consecutive occurrences and repeats it as a single value called the run length. The run length is followed by the value itself. The encoded output replaces the consecutive occurrences with the run length and the value pairs. Third is decoding. To decode the encoded data, the run length and the value pairs are reversed. The decoder reads each run length value pair. It reproduces the original data by representing the value the number of times specified by the run length. Let's understand this with an example. Let's say if input stream is AAA, BBB, CC, CC, DDD, AA. The encoded output should be 3A, 3B, 4C, 3D, 2A. Let me explain this. In the input, there are 3 consecutive occurrences of A, followed by 3 consecutive occurrences of B, 4 consecutive occurrences of C, and 3 consecutive occurrences of D, followed by 2 consecutive occurrences of A. Applying RLE encoding, we represent each run of consecutive occurrences by the run length followed by the value itself. The encoded output is 3A, 3B, 4C, 3D, and 2A. You can look on this example. Now, let's understand the advantages of RLE. First is simple and easy to implement. RLE is a straightforward algorithm that requires minimal computation. Second is efficient for data with long runs. RLE performs exceptionally well on the data that contains long sequences or repeated characters or symbols. Lossless compression. We saw that RLE allows for perfect reconstruction of the original data without any loss of information. Have a look on image on the bottom right corner of your screen. Instead of representing in a 4A, 4B, 4C format, we can use this representation also. W1, B1, W3, B3. So let's understand disadvantages of RLE. Limited compression for diverse data. RLE is not suitable for compressing data with minimal repetition or randomness. It is most effective when there are significant runs of identical values. Like you cannot represent Bhavya using RLE because BHAVYA, no character is repeated. Second is increased storage for no repetitive data. In some cases, RLE encoding may increase the storage size if there are no or few runs of repeated values. In such scenarios, the encoded data may require more space than original data. Second lossless compression algorithm is Huffman coding algorithm. Let's understand how it works through an example. Consider the input string BCCA, BBDD, AECC, BBAEDDCC. We know that ASCII value of these characters are between 65 to 97, and converting that ASCII value to binary will require 8 bits of storage for each character. And so the total storage occupied by this string is 8 into 20, which is equal to 160 bits, which is quite large. So Huffman algorithm used to save that space. It assigns variable length codes to characters based on their frequency of occurrence in the input string. The more frequent characters are assigned shorter codes, and while less frequent characters are assigned longer codes. Here is a detailed explanation of Huffman coding algorithm using the input string. Step 1, frequency calculation. The first step in Huffman decoding algorithm is to calculate frequency of each character in the input string. This is done by traversing the string and counting the occurrence of each character. Example, considering the input string BCCA, BBDD, AECC, BBAEDDCC. We know that ASCII value of these characters are between 64 to 97, and converting the ASCII value to binary will require 8 bits of storage for each character. So we discussed that earlier. So the frequency of each character would be A3, B5, C4, D4, E2. Okay. Step 2, building the Huffman tree. Next, we build a Huffman tree using the calculated character frequencies. The Huffman tree is a binary tree where each leaf node represents a character and its frequency. The construction of tree follows this step. Create a leaf node for each character, storing the character and its frequency. Sort the leaf nodes based on their increasing frequencies. Take the two nodes with the lowest frequencies and create a new internal node. The frequency of new node is the sum of frequencies of two nodes. Set two nodes as the children of the new node. Repeat the previous step until there is only one node left, which becomes the root of Huffman tree. You can have a look on this Huffman tree. Third step is assigning Huffman codes. Once the Huffman tree is constructed, we assign binary codes to each character based on their position in the tree. Moving to left child of a node corresponds to appending a 0 to the code, while moving to the right child corresponds to appending a 1. The Huffman codes are determined by traversing the tree from the root to each leaf node. Example, using Huffman tree from previous step, we assign the following codes to the characters A001, B10, C11, D01, E000. 4. Encoding the input string. With the Huffman codes assigned to the character, we can now encode the input string by replacing each character with its corresponding Huffman code. This results is a compressed representation of the original string. Example, using the assigned Huffman codes, the encoding string for BCCA, BBDD, AECC, BB, AEDDCC would be 101111 00110101010101 0001110100010000101111, and the space occupied by this is calculated from the table below, which is 45 bits. Decoding the encoded string. To decode the compressed string, we have to store the information that which code represents which character, and therefore the storage occupied by that can be seen from the above table, which is 40 plus 12 equal to 52 bits. The total bits occupied are bits message plus bits information for decoding is 45 plus 52, which is 97 bits, saving 63 bits. Okay, the original string has been encoded using assigned Huffman codes, resulting in a shorter representation that preserves the information and can be decoded back to the original string using the information table. The total bits occupied are bits message and plus bits information is equal to 45 plus 52, 97 bits. The original string has been encoded using the assigned Huffman codes, resulting in a shorter representation that preserves information and can be decoded back to the original string using the information table. Here are disadvantages of the Huffman coding algorithm. Huffman coding is a sequential encoding technique, meaning that to decode a specific part of a compressed data, the entire needs to be sequentially processed until reaching the desired section. This lack of random access can be disadvantage in certain applications. It requires the transmission or storage of the code block, which adds overhead and can be significant for small files and larger symbol sets. Huffman coding is suitable for encoding data with highly skewed or uneven symbol frequencies, as it many results in inefficient compression. You can have a look on this tree. Let's understand third lossless compression algorithm, which is LZW compression algorithm. LZW, Lempel-Zwiebelsch, is a popular lossless data compression algorithm that is commonly used for text and general purpose data compression. Developed by Abraham Lempel, Jacob Zwieb, and Terry Welsh in 1970s. LZW has been widely implemented in various applications, including image formats like GIF, file compression like zip, and network protocols like HTTP. The LZW compression algorithm works by building a dictionary of frequently occurring patterns in the input data and replacing those patterns with shorter codes. This process reduces the overall size of the data without losing any information. Here is step by step explanation of LZW compression algorithm. First, initialize the dictionary with all possible single character codes. Read the input data one symbol at a time. Initialize an empty string as a current pattern. Process the input data. Append the next symbol to the current pattern. Check if the current pattern exists or not. If the current pattern exists, continue appending the next symbol to the current pattern. If current pattern does not exist, output the code corresponding to the current pattern from the dictionary and add the new pattern to dictionary. Reset the current pattern to the last symbol read. Repeat step 4 until all symbols in the input data are processed. Output the compressed data, which consists of sequence of codes generated during compression process. Decompression. Initialize the dictionary with all the possible single character codes. Read the input compressed data one code at a time. Initialize an empty string as a previous pattern. Process the input data. A. Read the next code from the compressed data. Find the entry in the dictionary corresponding to the code. Output the corresponding pattern from the dictionary. If the previous pattern exists, create a new entry in a dictionary by appending the first symbol of the current pattern to the previous pattern. Easy, isn't it? Set the previous pattern as the current pattern. Repeat step 4a to 4e until all codes in the compressed data are processed. The output of the decompression process is the reconstructed original data. The LZW compression algorithm achieves compression by exploiting repetitive patterns in the input data. It dynamically builds the dictionary of patterns encountered during compression, allowing for efficient encoding or repeated patterns using shorter codes. As the algorithm processes, the dictionary grows to accommodate new patterns. Let's understand with an example. So, range of inputs is from 0 to 15. 0, 3, 0, 5, 0, 4, 14, 11, 0, 5, 0, 4, 0, 9, 11, 12, 14, 11, 15, 0, 5, 0, 4, 0, 9, 11, 11, 11. So as we can see, we need to store 19 digits as data. If we store them as they are, we require 19 into 4 is equal to 76 bits. Let's try to compress this data with LZW algorithm. We have range from 0 to 15. So our encoding will start from 16. Means dictionary elements will start from 16. So 0, 3, 0, 5, 0, 4, 11, 0, 5, 0, 4, 0, 9, 11, 12, 14, 11, 15, 0, 5, 0, 4, 0, 9, 11, 11, 11. So after applying all the steps, the compressed output will be 0, 3, 0, 5, 0, 4, 14, 11, 17, 0, 9, 11, 12, 19, 15, 21, 11, 28. Now by making dictionary, we can decompress this easily. Advantages of LZW compression. The LZW is a lossless compression algorithm, meaning that the original data can be perfectly reconstructed from the compressed data. It achieves a high compression ratio for text and other data with repetitive patterns. LZW compression is relatively fast and efficient, making it suitable for real-time applications. The LZW is widely implemented and supported by various software and hardware platforms. Disadvantages of LZW compression. LZW compression requires maintaining a dictionary which can consume additional memory. The compression ratio can vary depending on the input data, and certain types of data may not compress as effectively. LZW is subject to pattern restriction in some jurisdictions, which can limit its use and adoption. Overall, LZW compression is widely used and effective technique for lossless data compression, offering a balance between compression ratio and processing efficiency. Let's understand one lossy compression algorithm, which is JPEG. JPEG stands for Joint Photographic Experts Group and is a logic compression algorithm that results in significantly smaller file sizes with little to no perceptible impact on picture quality and resolution. A JPEG compressed image can be 10 times smaller than the original size. JPEG works by removing information that is not easily visible to human eyes while keeping the information that the human eye is good perceiving. Let's take a look at an overview of the steps that JPEG takes when compressing the image. So you can see these two images. There is a little difference, but the image on your right side is 10 times smaller than the image on your left side, and the image on your right side is JPEG image. Understand how JPEG works. First is high frequency details. Our eyes are more sensitive to changes in brightness and color in low frequency areas of an image, such as smooth gradients and large color transitions. However, we are less sensitive to high frequency details, such as fine textures or sharp edges. JPG takes advantage of this by reducing the amount of high frequency information in an image while preserving the important low frequency components. Color perception limitations. Our eyes have limitation in perceiving subtle colors differences, particularly in areas with high spatial frequency. JPEG utilizes this limitation by reducing the color information in such areas while maintaining the overall appearance of an image. There are total 6 steps in the JPEG algorithm. First is color space conversion. The first step is JPEG compression is to convert the input image from RGB color space to YCBCR color space. The RGB color space represents the color using combination of red, green and blue channels. The YCBCR color space represents the image into luminance component, which represents brightness, and the blue and red chrominance CB and CR components, which represents color information. The process is reversible and no data removed during the conversion. So these are total 6 steps. Color space conversion, which we have learnt just now, chrominance downsampling, discrete cosine transform, JPEG, fourth is quantization, fifth is entropy encoding, and sixth is JPEG decoding. Second step is chrominance downsampling. It removes a considerable amount of data. In downsampling, we take both blue and red chrominance component images and we divide the component images into 2 by 2 blocks of pixel. Then we calculate the average value of each block, remove the repetitive information and shrink the image. So each average value of a 4 pixel blocks takes up a single pixel. As a result, the information that our eyes are poor at perceiving, the red and blue prominence component images are shrunk to the 1/4 of original size, but the luminance remains the same. So before the image was 1 plus 1 plus 1 equal to 3, but now as luminance remains the same, which is equal to 1, but chrominance, both chrominance are 1/4 of original size. So the after size of image is 1.5. With just 2 steps, the image is half of the original size. Note that when resembling the picture, the blue and red chrominance images are rescaled to match the size of luminance component, with the RGB values being recalculated from Y, CB and CR. And because Y changes from pixel to pixel, the recalculated RGB values can change pixel to pixel as well. Third is discrete cosine transform. Well, essentially the discrete cosine transform go through each section of the image and find areas that have high frequency of alternating prominence or luminance. These elements that our eyes aren't able to perceive are then removed. This process is rather complicated, but bear with us. Let's use the luminance component image as our example, but know that the same process happens with the two chrominance components. The first step is to divide the entire image by 8 by 8 sections called blocks, each with 64 pixels with the values from 0 to 55 that represents luminance at every pixel. There is error prominence. Please replace this with chrominance. It is actually chrominance. There is typo here. Sorry for mistake. Okay. So next we shift each value by subtracting 128 from each value. So the range becomes negative 128 to 127 as you can see here in the picture. This step centers the frequency spectrum around 0, which improves the efficiency of the DCT. Negative 120 is black as you can see here, and positive 127 is white as you can see. Negative 120 is black and positive 127 is white, and 825x is the magnitude of this picture. The DCT is applied to each 8 by 8 block. The DCT formula is used to calculate the DCT coefficients for each frequency component of the block. The formula, as you can see, FUV represents the DCT coefficient at frequency UV. CU and CV are scaling factors defined as 1 by square root of 2 for U equal to 0 and V equal to 0, and 1 for all other values of U and V. FXY represents the pixel values of the 8 by 8 block. The double summation calculates the contributions of each pixel in the block to the DCT coefficient at each frequency. The result is a set of 64 DCT coefficients representing the frequency components of the block. You can easily understand this. Nothing in DCT actually compresses the image, but the next step, quantization does. It was very good point. Quantization. Here we have our table of constants corresponding to the utilization of each base image. The next step is to divide each value in the table of constant by corresponding value in the quantization table, round each result to the closest integer. So you can see here we are throwing away data, but really we are just throwing away data that our eyes don't perceive, so we can't even tell the difference. I've shown the previous image of bird. You can see there. You can go there again. This is quantization table and see 0 0 0 0 0. Only these are the values. So we divide this table by quantization table and we get this table. So 2 by 20 is nearly equal to 0. So we have put it 0 there. In this step, now we have two matrices containing integer values from block 64 pixel, one for luminance and one for chrominance. Perfect. We use zigzag pattern. So fifth is entropy encoding. Now all that is left to do is to list the values that are inside each matrix. Run RLE. So we are running RLE right now. Run length encoding, which we have learnt before just now. Since we have a lot of zeros, and then run the Huffman coding algorithm before storing the data. So if we run like this, so we encounter 3 zeros here, then we encounter some digit, then we encounter 3 zeros. Instead of doing this, we just encounter first all positive and negative digits, then we are remaining with only zeros. So what happens is we can reduce the storage. Got the point? RLE and Huffman coding are lossless compression algorithms that reduces the space needed to store information without removing any data. We have learned that. As you can see, the result of quantization has many zeros toward the bottom left corner. To keep zero redundancy, the JP algorithm does a zigzag scanning pattern that keeps all zeros together. We can understand this. After zigzag scanning, we get a list of integer values, and after running RLE on the list, we get each number and how many times they are repeated. Finally, JPEG runs Huffman coding on the result, and values that have more frequency like zeros are represented with fewer bits than less frequent values. 6 is JPEG decoding. Whenever we open a .jpg file using an image viewer, the file needs to be decoded before it can be displayed. To decode a JPEG image, the image viewer does all the above steps in reverse order. Run Huffman, Huffman decoding on the file data, deconstruct RLE, put the list of numbers into 8 by 8 matrix, multiply integers value by corresponding quantization table, multiply the weight values by corresponding base images, the sum them up to get the pixel values, upscale the chrominance channels, change the color space from YCBCR to RGB, and then it displays the image. Isn't that fascinating? Yes, it is. I hope you enjoyed my video on data compression. It's a complex topic, but I did my best to break it down and make it easy to understand. It was great fun for me. If you found the video informative and helpful in unraveling the mysteries of data compression, hit that like button. Thank you for watching. This is Bhavya Patel signing off and leaving you with a spark of inspiration to light your way.